All right, let's talk about something we almost never think about, the air you're breathing right now. Did you know there's a hidden code that governs how it behaves? It's a simple formula, PV equals nRT, and it's behind everything from the weather to technology that literally saves our lives. But to really get it, let's start with a puzzle. Think about a car's airbag. In a crash, this fabric bag has to explode out of the dashboard, perfectly cushion a person flying forward, and then just as quickly, get out of the way. I mean, how is that even possible? Get this, the whole thing happens in just 30 milliseconds. That is way faster than you can blink. And it's not magic, it's an absolutely incredible feat of controlled chemistry and physics. So what's the secret? Well, the magic behind this incredible life-saving device is all about a perfectly calculated chemical reaction, a reaction that is controlled by one single, beautiful equation. It all starts with this tiny pellet of a solid chemical called sodium azide. And here's the real challenge for the engineers. How on earth do you turn this little solid pellet into a 60-liter cushion of gas with perfect split-second timing? The solution is just brilliant. It's a three-step chemical chain reaction. First, an igniter triggers the sodium azide, which instantly turns into a huge cloud of nitrogen gas. That's what fills the bag. But it also creates super toxic sodium metal. That's where step 2 comes in. Potassium nitrate is right there waiting to instantly react with that dangerous sodium. And bonus, it creates even more nitrogen gas. Finally, step 3. A little bit of silicon dioxide, which is basically just sand, reacts with whatever is left over to form a harmless, stable blast. All the dangerous stuff is neutralized before you ever come into contact with it. And figuring out the exact amount of that initial solid you need, not too much, not too little, well, that's calculated with perfect precision using one of the most fundamental laws in all of science. So, it's time to pull back the curtain. Let's deconstruct that very law and get to the heart of how scientists and engineers can so perfectly predict the behavior of gases. And here it is, PV equals nRT. You've probably seen it before, maybe in a high school science class. It's known as the ideal gas law. And what it does is describe this beautiful relationship between 4 key properties of any gas. Let's break it down really quick. P is for pressure. That's the push the gas has on its container. V is for volume, the space it takes up. N is the amount of gas you have, the stuff. And T is for temperature, which is just a measure of its heat. Okay, but what about that R? Well, R is called the ideal gas constant. And the best way to think about it is as a kind of universal translator. It's the one number that makes sure all the different units for pressure, volume, and temperature can speak the same mathematical language so the whole equation works out perfectly. An equation this important doesn't just appear out of nowhere. It was actually pieced together over almost 200 years by different scientists, each one solving a little piece of a giant puzzle. The story starts way back in 1662 with Robert Boyle. He's the one who figured out that if you squeeze a gas, increase the pressure, its volume gets smaller. Makes sense. Then, over a century later, in 1787, Jacques Charles discovered that if you heat a gas up, it expands. Then, in 1811, Amedeo Avogadro figured out the obvious but important part: the more gas you have, the more space it takes up. Finally, in 1834, a guy named Émile Clapeyron looked at all these pieces and put them together into the one unified law we still use today. So we know what the law is, but the really interesting question is, why? Why does it work so perfectly? To understand that, we need to zoom way, way in, down to the microscopic world of the molecules themselves. The answer lies in something called the kinetic molecular theory. Now, it sounds fancy, but the idea is actually pretty simple. It just asks you to imagine that a gas is really a collection of zillions of tiny particles, like microscopic billiard balls, all zipping around randomly and crashing into each other and the walls of their container. In a perfect or ideal gas, they don't lose any energy when they collide, and they don't stick to each other at all. And here's the aha moment. This theory is what connects that invisible microscopic dance to the world that we can actually feel and measure. That pressure we feel, that's just the combined force of trillions upon trillions of those little particles smacking into a surface. And temperature, that's nothing more than the average speed of those dancing molecules. The faster they move, the hotter it is. So what this all means is that PV equals nRT isn't just some handy summary of experiments. Nope.
It is the direct mathematical consequence of what happens when billions of tiny particles all obey the basic laws of motion. It's physics, right from the ground up.
Okay, that's enough theory. Let's bring this all back down to earth and take a look at where else this hidden code is secretly running things in your everyday world.
Now, I gotta give you a quick disclaimer. There's no such thing as a truly ideal gas in the real world. Real gas molecules do have a tiny bit of volume, and they have very weak attractions to each other. But for almost everything we deal with day to day, the ideal gas law is shockingly accurate. For instance, let's go back to your car's tires. The volume, the space inside the tire, is more or less fixed, right? Well, according to the law, that means pressure is tied directly to temperature. So when it gets cold outside, the air molecules inside your tire slow down, they don't hit the walls as hard or as often, and your tire pressure drops. In fact, there's a really useful rule of thumb you can remember. For about every 10-degree Fahrenheit drop in temperature, your tires will lose about 1 psi of pressure. It's the reason your tire pressure light almost always seems to come on during the first really cold day of winter.
Or what about weather balloons? This is another great one. Scientists only partially inflate them on the ground. Why? Well, as that balloon goes up and up, the atmospheric pressure outside gets lower and lower. So to keep things balanced, the gas inside the balloon has to expand into a much bigger volume. If they filled it up all the way on the ground, it would pop long before it reached its target altitude.
So, from an airbag saving your life in a crash to a weather balloon high in the sky, PV equals nRT is this simple, elegant code that describes the complex, invisible world of gases. Which really leaves you with a final thought, doesn't it? Now that you know this code, what other invisible forces, all governed by simple rules, are shaping the world around you at this very moment?